Alrighty, in this video we are looking at using exponential functions. Our objectives are to write exponential functions to model real-world situations such as exponential growth and decay, and to use exponential functions to solve problems. So this is where we actually get to take a look and see how these are utilized in our everyday lives and how they model what's happening around us, which is, I think, pretty cool. So in this first example, we're just kind of learning some strategies. We want to write the exponential function in this form, y equals ab to the x, whose graph passes through those 2 points. Well, to be able to do this, we need to know the a and the b values. And what we'll do is we'll substitute these values that were given, the x and y coordinates, into that form to create a system of equations. Let me show you. This is the form. This would be the form after we've plugged in that first point. The y value is 12, and then it would be equal to ab to the second power because our x value is 2. Similarly, our second point would look like 96 equaling ab to the 5th power because our x value is 5 and our y value is 96. So now that we have those two equations, we are going to solve our system. Solving the system means finding a and b. So we're going to take this first equation and solve for one of our variables. Now that we know what a is equivalent to, we can plug that into the other equation. We're using substitution. And we'll plug what a is equivalent to into the place where a was. So now it's 96 equals 12 over b squared times b to the 5th. That's substituting into the second equation. We can simplify that. It would be 96 equals 12 to the 12 times b to the 3rd. Using our properties of exponents, we did so. And then dividing each side by 12 gives us 8 equals b to the 3rd. And there is only one value that when cubed gives you 8. It is 2. So now we know our b value is 2. The only thing remaining is to find the value of a. So we'll plug 2 into our equation where a was isolated. So that's 12 divided by our b value, which is 2 squared. That's 12 over 4, which gives us 3. We can now write the exponential function substituting in these values for a and b. And that would give us y equals 3b, which is 2 to the x. I have a definition for you here. Functions that look like this, y equals a, and then in parentheses 1 plus r, and then raised to some x power, they model exponential growth when your r is greater than 0, and exponential decay when your r is between -1 and 0. So let me go a little bit further in depth on what this equation means. When in the context of exponential growth and decay, which is a very prevalent model in the science fields, the a value is representative of an initial amount. It could be an initial amount of money, it could be of some amount of a substance. It really varies. The R is going to represent the percent of change, and it will be in a decimal format. You won't actually see a percent, like 50% in there. It'll be written as 0.5. X represents the time period of whatever we're working with when it comes to the time of growth or the time in that decay model. And we have something called the growth factor. It is what is inside of those parentheses, and it is our B value. If you think back to just the regular form for an exponential equation, it's a b to the x. Well, our b represents our growth factor, and it is 1 plus your rate. So let's take a little look here at this example. We're going to complete a chart where we're going to look at the initial amount, rate of change, growth factor, and the type, being exponential decay or growth, for each one of these functions. So let's look at that first one. At letter A, the initial amount is our A value, which would be 10. Our rate of change is 0.5, which, if we were to write that as a percent, would be 50%. The growth factor is 1.5, and this is an exponential growth because for every unit of time, it grows by 50%, each unit of time. Now, looking at problem B, our initial amount is 45. The rate of change, notice that now it is negative, so it is a negative 0.25, which would be negative 25%. The growth factor would be the sum of what is inside parentheses, and that is 0.75, and that gives us a decay. It is decaying by 25% each as time increases. In our third equation, the initial amount is 20,000. But the rate of change is not so easily seen because it is not in the form 1 plus or minus r. But we could manipulate it so that it is. 1 minus 1/2 gives you 1/2. So all we've done is a little bit of mathematical operation here so that it is in the form that we desire. What we have just flashed onto the screen is exactly the same as what you see there for problem C. So now that it's expanded like that, we can see that we are working with a rate of change of negative 1/2, which would be negative 50%. And the growth factor was pretty evident to us initially. It was 1/2. And this is, once again, a decay model because our rate is negative. Looking at problem D, it's not really in the form that we need to be able to identify all of this information, but we can manipulate it. It is 3 being raised to the exponent there, but 3 is the same thing as writing 1 plus 2. Now it's in a format that is more beneficial to us. And that A value, well, there really isn't 1. So it is 1. It wouldn't be 0 because if you multiplied 0 times anything, that whole thing would zero out. So it's just an almighty 1. You don't see him, but he's there. This means our initial amount is 1. Our rate of change is 2. But ladies and gentlemen, that if you then try and write 2 as a percent, you move that 2 place that decimal 2 places to the right, that becomes a 200%. And this is going to be a growth factor of 3, and it is a tremendous exponential growth model because it is growing by 200%. I would guess that the D represents days because it's supposed to measure time. So quite a tremendous growth there. So I hope that that is helpful in explaining how you can determine exponential growth or decay given any kind of equation or function. That's all. Thank you.